Hello, this is the first lecture of a three-lecture series about the physicochemical properties or the physicochemical basis of biochemical interactions. We will start with very fundamental and basic chemical rules, and because even though the chemical properties of living organisms, the biochemical reactions, seem to be quite different than the chemistry of inorganic compounds. The basic principles governing both chemical reactions are very similar. People did not think that way for a long time. The chemists believed that the rules of chemistry governing the living organisms and the inorganic, non-living organisms are quite different. For a long time, this belief was very popular among the chemists, until this gentleman, Friedrich Wöhler, in the 19th century, synthesized a so-called organic molecule, which was believed to be synthesized only by living creatures. He synthesized urea from completely inorganic molecules in a test tube, without the help of any living organism. So by this experiment, the belief in that the organic chemistry has different rules and principles than inorganic chemistry was out of fashion, and the modern biochemistry was born. Now we believe that the basic rules for biochemical and inorganic chemical reactions are basically the same. The only difference is the molecules. The molecules are different. Organic molecules, or the molecules the living organisms use for their chemical reactions, are much more complex than the inorganic molecules. But the basic rules are the same. So we will basically concerned about these four atoms or elements. Of course, there are other elements involved in biochemical reactions, like phosphorus, iron, and things like that. But those four elements are the most common basic elements we will see in organic and biochemistry. The first thing the chemists want to know is how elements or atoms come together and form molecules. Because not every molecule is stable. Some molecules are stable, some others are not. So a rule that will predict which molecules are stable and which molecules are not stable will be very, very useful for the chemist. So one such rule or one such principle is called the Lewis rule or Lewis principle, which brings us to Lewis structures of the atoms. The Lewis rule tells us that atom is in stable configuration if the outer shell of that atom resembles the outer shell of the noble gas at the end of that row in the periodic table where the atom resides. For example, hydrogen has one electron, and on that row the noble gas is helium. So if the outer shell electronic structure of hydrogen resembles helium, then the hydrogen molecule will be stable. For carbon, nitrogen, oxygen, you see that the carbon has 4 electrons on its outer shell. nitrogen has 5, and oxygen has 6. And they are on the same row in the periodic table, and the noble gas at the end of that row is neon. And neon has 8 electrons in its outer shell. So if these 3 atoms, or the elements, carbon, nitrogen, oxygen, resume the electronic structure of neon, then they will be stable. However, they lack sufficient electrons to do so. So they share electrons between them. So each of the elements will acquire an electronic structure similar to the relevant noble gas. For example, compounds or molecules, as shown here, are stable because, as you can see, the CH4 molecule on the left-hand side, for each hydrogen, as they share the electron with carbon, now they have 2 electrons on their outer shell, which makes them look like helium. And the carbon, as it shares 4 electrons with 4 hydrogens, its outer shell electronic structure looks like neon. So both the 4 hydrogens and the carbon are stable. So this compound is stable according to the Lewis rule. The red dot is the electron coming from the hydrogen, and the black dot is the carbon's electron. So it's a similar thing for the other 2 compounds. One is NH3, and nitrogen needs 3 hydrogens to form a stable structure, because it lacks 3 electrons on the outer shell to resemble the electronic structure of neon. And oxygen requires only 2 electrons to resemble the electronic structure of neon. So H2O and NH3 are stable molecules, and this electron sharing is called covalent bonding in chemistry. So what are the orbitals these electrons occupy? We know that the outer shell of carbon has 4 orbitals, 1 s orbital and 3 p orbitals, p, x, p, y, and p, z, it's called. The total capacity of 8 electrons, 2 in the s and 6 in the p orbitals. And however, there are only 4 electrons in the outer shell of carbon. So what is the distribution of these electrons? 2 in s and 2 in p orbitals, 1 in s, 3 in p orbitals. That is an important question. However, the thing is more a little bit complicated than it looks, because there is something called hybridization of the electronic orbitals. The shape of the s and the p orbitals are shown in the red box. The s orbital has a spherical structure. The p orbital has 2 lobes. The green thing is the p orbital, but it's not 2 orbitals. Actually, it's a single orbital. It has 2 lobes. So these 2 orbitals can hold up to 2 electrons. But it turns out that sometimes these 2 different orbitals hybridize and form 2 identical orbitals. Instead of 2 different orbitals, you end with 2 identical orbitals. They are called hybrid orbitals, and there is sp hybridization. What happens is 1s and 1p orbital hybridize into 2 sp orbitals. One of the 3 p orbitals goes into hybridization, and the 2 p orbitals are left as they are as is. So it ends up with something like this. Instead of 1s and 3 p orbitals, you end up with 2 sp hybrid orbitals and 2 p orbitals, which did not change. This is called sp hybridization. There's also something called the sp3 hybridization. In this case, 4 orbitals to 1 s orbital and 3 p orbitals, they all hybridize into 4 identical hybrid orbitals. They are called the sp3 hybrid orbitals. The net result of this is, instead of 1s and 3p orbitals, you end up with 4 sp3 orbitals. All of those sp3 orbitals are identical. So what happens is the carbon goes into a hybridization, either sp3 or sp hybridization, or sp2 hybridization, as we will see soon. If it goes into sp3 hybridization, the carbon now has 4 on its outer electronic shell, 4 identical orbitals, which combine with hydrogen, 4 hydrogen atoms, as we've seen previously, to resemble the electronic structure of neon, and for hydrogen to resemble the electronic structure of helium, and it ends up with the CH4 molecule, as we've seen previously. However, there is an important point here. As these 4 orbitals, hybrid orbitals, are identical, so the structure of these orbitals are absolutely symmetrical. So the angle between each of them is the same. This is called a tetrahedral structure. Okay, and so the bonds, the chemical bonds formed between the hydrogen and carbon, 4 bonds, covalent bonds, has a 3-dimensional structure which is called a tetrahedral structure. Okay, so this is the summary. There are 6 hydrogen and 2 carbons. The Lewis structure are shown on the left-hand side. They combine to form a stable compound due to Lewis rule. And each electron sharing is called a covalent bond and is sometimes represented by the line, as seen on the right-hand side. The molecules is ethane and C2H6, the molecule is. And the 3-dimensional structure is not planar as suggested by the formula, but the 3-dimensional structure is 2 tetrahedral carbon molecules combined together, which has a 3-dimensional structure. So the tetrahedral structure of methane can be seen in ball and stick configuration much better, clearly. The ammonia has only 3 covalent bonds. Blue structure with 2 dots in it is the orbital, which is full, which cannot form covalent bonds. However, the tetrahedral structure is pretty much preserved. It's also the same for water. Water has 2 orbitals, sp3 orbitals, which has 2 electrons in it, which cannot form covalent bonds. However, the 3-dimensional structure of all these orbitals, the covalent bond orbitals and also the full orbitals, which cannot form the covalent bonds, has the tetrahedral structure due to sp3 hybridization. So in all of these molecules, the carbon, nitrogen, and oxygen, they have sp3 hybridization. As I told you before, there is also something called sp2 hybridization, which is kind of more important than sp hybridization. sp3 hybridization is very common in organic chemistry, as we've seen. A lot of molecules, from water to ammonia to many carbon compounds, has sp3 hybridization. But sp2 is also very important. It is involved in double bond formation. What happens here is that 3 orbitals, 2 p orbitals and 1 s orbitals hybridize and form 3 completely symmetrical orbitals called sp2 hybrid orbitals, and they kind of lay on a planar surface as shown here, and the single p orbital, which does not hybridize, is perpendicular to the plane formed by those 3 hybrid orbitals as shown below. There's a 90 degrees angle between the long axis of p orbital and the plane formed by the sp2 hybridized orbitals. This has some important implications. When 2 carbon atoms, which are sp2 hybridized, form bonds, they form 2 types of bonds, covalent bonds. One is shown here in blue. The 2 sp2 hybrid orbitals, one from each carbon, form simple sigma bonds. They overlap. The blue orbitals overlap, share electrons, and form a simple sigma bond covalent chemical bond. However, the p orbitals, which are perpendicular to this blue sp2 hybrid orbitals, can also form another type of chemical bond, covalent bond. It's called the p bond. So the p bond is the green area in the picture. Be careful that they are not 2 separate orbitals. The green orbital is a single one. It has a donut shape. The upper part and lower part is the same orbital. There are 2 electrons in it, and they occupy that space. It's called the p orbital. The other 2 sp2 hybrid orbitals left behind can also form sigma bonds with hydrogen or with other carbon compounds, whatever. But all of them, all those 4 hydrogens, 2 on the left side and 2 on the right side, they all lie on the same plane. Okay, and this bond cannot, this double bond, do not allow the molecules to rotate on the long axis of the bond. The sigma bonds, as they are symmetrical around the long axis, allow the molecule to rotate around the long axis of the bond. However, the double bond, as you can see, cannot be rotated, because if you try to rotate these 2 sides of this molecule, you have to break the p bond. The sigma bond, it will be okay, but the p bond will break. So this is why the double bond actually prohibits the rotation around the double bond. So this is another representation of a double bond. The double bonds are usually shown like 2 identical lines, but they're not identical as we've seen before. One of them is a sigma bond, one of them is a p bond, 2 different types of bonds. But the molecule forms a planar structure. The sp2 hybridization, because of its nature, has a planar structure, as we've seen before. Okay, this is the tetrahedral sp3 hybridization. The blue-green thing is the carbon, and the white spheres are the hydrogens, and the sticks in between them represents the sigma bonds. And this is an sp3 hybridized carbon with 4 hydrogens, and it has a tetrahedral structure. Tetrahedral structure is a 3-dimensional structure. If you put it on a table, the 3 hydrogens will sit on the table, but the 4th hydrogen will stick either out of the table or into the table. Okay, so this is an important issue. But in actuality, the molecule has a volume, which is called the van der Waals volume. What happens if two atoms that form the covalent bond has different electronegativity? If the electronegativity of those two elements are close to each other, electrons shared by these atoms are shared evenly, more or less. If this is a carbon-carbon bond, it's completely even sharing. However, if one of the atoms is more electronegative than the other, for example, here the oxygen is more electronegative, it means that the electrons are not shared evenly, or one of the atoms attracts the electrons more towards itself, and one atom kind of loses part of its charge to the other one. This is called a polar bond, covalent bond, and here it's shown by this arrow. Hydrogen loses its electron partially to oxygen, and it causes a partial charging of hydrogen, positive charging of hydrogen, and a partial negative charging of oxygen. It's called partial because it's not full electronic charge. The hydrogen did not lose its electron completely. It only partially loses it. If the electronegativity of one of the atoms is much larger than the other one, then the electron completely breaks off from one and leaves one and goes to the other one. So one is charged negatively and the other one charged positively. So there is one net electron charge lost from one and gained by the other. You can see it here in sodium chloride molecule. This then called the ionic bond. So and there are compounds in between, like hydrogen chloride, HCl. The HCl bond is still polar covalent bond, but it's almost on the border of being an ionic bond. As you can see, the polar bond is a dipole. Dipole is a system of charges where the total or the sum of the charges is zero. There is no net charge. However, due to the separation of the positive and negative parts, they are not on top of each other. They are separated by the length of the bond, chemical bond. This structure has an electrical field around them. However, dipoles are vectors, as in other vectors in physics. The two dipoles has to be added as vectors. So if the two dipoles are on the same axis and their strengths are the same, their summation ends up with zero net effect. However, for example, carbon tetrachloride has 4 very polar bonds. However, when you add them together with vector addition, they give you zero net dipole moment. Carbon tetrachloride is a non-polar molecule, even though its 4 bonds are extremely polar. However, in water, the hydrogen-oxygen bond is polar, but it's not as polar as carbon chloride bond. However, because these two bonds are not on the same axis and they have an angle between them, the vector addition sum of these two dipoles give you a net dipole moment, which makes the water molecule a very polar molecule. it has a dipole. The water molecule, contrary to the carbon tetrachloride molecule, has a strong dipole. This brings us to another important property or an important issue, the solvation in water. Here you see a crystal structure of sodium chloride. Here you can see that the chloride and sodium atoms are held together by ionic bonds. And these ionic bonds are extremely strong, so sodium chloride has a very high melting point. However, if you put it into water, suddenly this binding force between the atoms goes away, and the sodium chloride atoms dissolve. This strong ionic bonds holding them together in the crystal structure and make it a very hard solid suddenly loses its power, and the ions, the chloride and sodium ions, starts to show diffusion and start to act like fluid molecules. This is due to deep dipole, net dipole of the water, and water has some property called the dielectric property. The water is a dielectric liquid. I show here a schematic representation of the H2O dipoles. It has a positive side and a negative side, and actually when you have no electric field around, the water molecules are oriented randomly, so there is no net dipole of liquid water. However, if you put water into an electrical field, if you apply an electrical field, these dipoles orient themselves according to the electrical field. And you can see that the positive charges tend to turn towards the negative end of the electrical field, and the negative ends of the dipoles turns to orient themselves toward the positive end, which at the end gives a completely opposite electrical field. You apply one electric field and the molecules orient themselves, and they give you an opposing electrical field, because when all dipoles has the same orientation, now their vector sum ends up giving a non-zero dipole moment. So this explains how sodium chloride bond, the ionic bond between the sodium and chloride molecules get weakened, because if water goes between sodium and chloride molecules, the electrical attractive force, the electrical field, gets weaker, so the molecules, the ions cannot attract each other as strongly as they are in vacuum or in crystal, and they start to move separately, individually, and start to diffuse. This is called solvation of sodium chloride in water. So this is end of the part 1. We will continue with the macromolecular structures in the second hour.